Yeah, so hello everyone, welcome to all. So our today's speaker is Dr. Annapurna Banik, and she will continue her lectures on subharmonic and plurisubharmonic functions. So Annapurna, over to you.
Yeah, thank you, Abhishek, and sorry everyone for the long delay. So I gave my
Yeah.
first lecture like 2 months back. Then I took long time to resume again. So yeah, my apology for that. So yeah, I have I just briefly wrote down what was done last time. So it was very basic was discussed in the last time. But yeah, the I mean. So basically my emphasis was on how one can see subharmonic functions with some less abstract object. That's why my emphasis was on discussing the analogy between subharmonic function and convex function, and of course I defined subharmonic functions, and I discussed very basic properties of subharmonic functions. Now, I mean, this is not really a course on this potential theory of pluripotential theory, so it's difficult to talk about all kind of properties, examples of these functions. So I mean, that's very hard to do in like 2 or 3 lectures. So if you are very interested in all these subjects, I mean, please read some textbook. There are many standard textbook on these subjects, and also be very careful because there are a lot of interdependencies of the results basically when you read these things. So I mean, in this lecture I will feel free to use various results. I will not be very careful about the order of dependencies, like which results depend on which. I mean, that's not doable on these 2 or 3 lectures, but I will feel free to use many results basically, and if possible I will try to say some interdependencies. But yeah, I mean, basically although I define subharmonic functions and discuss very basic properties, many important properties are not discussed, and I will not get the chance to discuss that. But I mean, please have a look in any of your basic textbooks. So this is what I defined last time. And so as I said, there are many important properties which I will not get chance to discuss. But so today what I will try to start with, so this is something is probably known to everyone. So I will talk about some characterization of subharmonic functions. So this is known to everyone, I think. So if I start with some C2 smooth function, then you know that this is one easy way to see subharmonic functions, that U is subharmonic if and only if you can compute its gradient, and that is basically non-negative, right? So I hope everyone has seen this thing. But the way subharmonic functions are defined, so it is defined in terms of some sub average property or sub mean value property, right? And a priori I did not, or I mean we did not, don't assume U to be C2 smooth. So it is defined for any upper semi continuous functions, right? So today I want to start with that what happens if uh, we go beyond this regular class C2. So what happens if you start with any arbitrary subharmonic function? So do we have some nice characterization as I just wrote? So the good thing is, yes, we have. And I mean, so for that you have to go beyond this classical derivative, and we have to talk about distribution. So that's what I have to, as that part I have to assume that you have some familiarity with distribution theory. So what happens is I start with some subharmonic function. So this be arbitrary. So again, a fact which I did not mention last time. So fact is, if you start with any subharmonic function, you can prove that this is basically locally integrable. So as long as you have a locally integrable function, you can define the various order derivatives of u in terms of distribution. Okay, so that's why I mentioned that this L1 log requirement. Then you can define in the sense of distribution, right? So the nice part is, I mean, the definition part is clear. So what happens is, even if you define this uh, gra- uh, this gradient of, sorry, this is not gradient, this is Laplacian, I'm so sorry. So Laplacian is this I mean summation over this del 2 del x j del x j square. So what happened is, you define this Laplacian in the sense of distribution, and you still have the fact what you have for C2 smooth function. So that's what I will state, that if you start with a subharmonic function arbitrary, then this uh, Laplacian u, this is positive in the sense of distribution. So the whatever we knew for the classical sense is still valid. Now, what do you mean by positive in the sense of distribution? This simply means, if you take any test function which is non-negative, then the action of this del u over phi is positive. Okay, but the nice part is the converse is also true. So what do I mean by that? So conversely, if I start with a if I start with a distribution, so if so how should I write, let me see. So if t be a distribution, and please recall, I mean, for L1 log function, you can talk about the derivatives in the weak sense. Similarly, for distribution also, you can talk about derivatives. So, so my assumption is, if I have a distribution and this del t, so this del t you have to interpret in the sense of distribution again, and you have that this del t is 0, then there exists a unique subharmonic function such that this that subharmonic function has some nice association with this distribution that I start with. That is to say that tu equal to t, which means for any test function, the action is like tu of phi. This is just will be seen as uh, integration phi u dv. This is what it means. So the point of this discussion is, for arbitrary subharmonic function, we still have the nice characterization, what we knew in the classical sense. Now, right. So, I mean, why do we talk about this, all these things, right? I mean, because I mean, like, at least in the context of complex analysis, we do want to uh, consider the functions, subharmonic functions like log mod z, right? So these are very key examples of subharmonic functions, at least in our context. So, sorry, I mean, I think I did not give any examples, but of I probably have no. So log mod z. So in domain of C, I am saying, so given, I mean, okay, I don't need don't need to be planar. So let me quickly write. So for any holomorphic function in any domain, basically, which is same as, so here I have not talked about any complex analysis so far. So you start with a domain in Cn, which is just R2n, and suppose your function is not identically equal to 0, otherwise you will you can't talk about log mod. I mean, you don't want to consider identically minus infinity function. Then it is a very standard example that log mod f is subharmonic over this domain. Okay, so now, so for example, if you are in one dimension, for n equal to 1, log mod z is our favorite example of subharmonic function. And this is of course not C2 smooth. In fact, it does have singularity at as long as the corresponding holomorphic functions are vanishing, right? So now I talked about this characterization. So it's a good idea to see one example probably. Okay, but is this blocking my screen, right? I can get rid. Okay, yeah,
Yeah.
this is gone. Yeah, this is fine. Right. So, I mean, since I discussed this theorem one, let me give some example. Like, I mean, why is this a real theorem? I mean, this is not just for sake of theory, you know. So suppose now I'm considering planar domain. So suppose my subharmonic is say log mod. So I am in C. Okay, so in C. So this is an example of subharmonic function in C. A is some fixed complex number. Okay, so this is subharmonic. So this is not smooth as you can see. So but this is subharmonic. So what is del u, I can ask. So del u makes sense, just I discussed. So the I mean, this is a nice exercise you can try, which is not very straightforward. I would say this, you have to do serious computations, but yeah. So you can show actually that this delta u, where u I just wrote, this is just 2 pi times Dirac mass at the point A. And what I mean, why I mean, this A is not a magic. A is basically the point of singularity of my function. Okay, so that means simply for any test function you start with, the action of this del u distribution, this will be just 2 pi times the function phi evaluated at A. Okay, so this is a nice object. So but this actually kind of justifies the theorem I stated, that I mean, you do have some real I mean, you have to see this del u, I mean, not as a function but something much beyond that function. Okay, so in fact something once you know this thing for log mod z minus a, this is not hard to show that if you start with a holomorphic function in a planar domain I'm talking, and this is not identically zero, then you can also compute the this del of log mod f, and can you guess what will happen? This will be basically let me check once. Mm, yeah, so this will be basically so basically I'm taking a summation over the zero set of a. Okay, so as long as f vanishes, this log mod f has a singularity, and these singularities are captured by this the corresponding Dirac masses, and mfa is basically the order of vanishing of f at a. So yeah, this is what I wanted to discuss. Yeah, let me any questions so far? Okay. Right. So the I mean, so far I had told that you can see this Laplacian U as a distribution. Okay. So, but yeah, I mean, distribution is again, I mean, something abstract object which you can't get rid of because my underlying function is not smooth enough. But you can get something little more familiar when you start with a subharmonic function. So what do I mean by that? So let me state a fact. So I mean, you can have some special kind of distribution when you start with some subharmonic functions. So I will see what I'm saying. So right. So where is my theorem that will be relevant basically? So yes, so what I stated is this del u is a positive distribution, right? So what do I, so that means is if I start with some subharmonic, then del u is 0, which means when you see this action over all test functions. So how do we define this? This is just nothing but u del phi with respect to the Lebesgue measure, and this is known as 0, right? So, this is something we have specially for subharmonic functions. This positivity is coming for subharmonic functions. Please keep that in mind. Now, my fact is that any now what is a distribution? So distributions are so del u is my distribution. So this is a priori is a continuous linear functional from CC infinity, right? So I don't know, this is defined all, I mean, so CC infinity is contained in CC omega, class of all continuous compactly supported function. Okay, so a priori I don't know whether this distribution is defined all over these bigger spaces or not. But since I happen to know that this distribution is positive, so I will state another fact, that any positive distribution is actually belong to the dual of C omega CC omega, which that means, that is to say that this will extend to the bigger space. So a priori it was defined on this smaller space. So we will get extension on this bigger space. So this del u can be seen as a functional over this bigger space. Now, does this remind you something? So you might have in your measure theory course or functional analysis course, you have heard about this representation theorem. So having this fact, you can see these positive distributions as a measure. So this positive distribution, say t is basically a positive Borel measure, and this is by the Rees representation theorem. So what's the moral of this story is, so if I start with any subharmonic function, this Laplacian of u in the sense of distribution, this is basically giving me a measure, right? So that is the moral of story. So you can associate a nice measure in, so this is not any random measure. This is, okay, I should not say the word random. So this is not any arbitrary measure. This is a positive Borel measure that you can associate to every choice of your subharmonic function. So that is the moral of the story. And the example I stated, I didn't prove. So in this example, you can actually see that, I mean, so although my discussion was about distribution, but you can, in this explicit example, you can actually see that how the measure actually looks like, right? So yeah, that's what that is something something to keep in mind. And yeah, so this association of subharmonic function and measure is kind of very important. So not, maybe not today, but like in the final lecture, I will again I will sort of come to this point and make some remarks about that why I mean it's important to see this Laplacian of u as a measure. Okay, so right. Yes, so I already stated the example. Right. So yeah, I did various discussion on subharmonic function. I also gave this characterization. Now I will probably slowly move to the part on the solution of Dirichlet problem for harmonic functions in the domains in Rn. So This is a slightly, I mean, okay, yeah. So, so again, how can we see subharmonic functions? Okay, so in the classical sense, at least, just keep this classical Dirichlet problem in mind. So, you want to solve this PDE. This is a PDE. So this is you can see Dirichlet problem on some domain in Rn. So you want to solve this PD, okay? And how? What are the solutions of this PD? Those are precisely harmonic functions. So okay, I have written very badly. So this Laplacian is zero on the domain, and I want to assign some boundary value on the boundary. Okay, so this is my PDE, and the solutions of this PDE are precisely all harmonic functions such that its boundary value is f. Okay, so in the classical, in the ball, it is very much solvable, it is solvable, so which is kind of very classical. So I will in after 2 minutes I will also briefly state a solution of the ball, but let's try to understand what are we doing and what are the connection of solving this PD with subharmonic functions. So a solution of this PD, so maybe star solutions are harmonic functions, but from the PDE perspective, it's not always possible or doable to. At once you may not be able to solve this PD. Okay, so what instead in PD perspective is done? People seek for sub solutions. So for seeking solutions of star, one may need to appeal for, say, subsolutions. And what are subsolutions typically mean? So I have this operator u, so I may not get zero, but I would get some inequality instead. So like this, and this u may not match on the boundary with f, but this will be at least dominated by f. So these functions of these forms are typically called subsolutions. So whatever we have definitions we have seen, you can think think the following, that subharmonic functions are basically subsolutions for when you try to solve this PD star. So, and this discussion, this approach is kind of important when we want to solve this PD, not in ball but over more general domains. So this is known as parents method that we will talk in a moment. So yeah, so having this discussion, we want to solve star in a general domain. So, not general domain. So for now, let's talk about bounded domain in Rn. So of course, it will not be possible to solve this PD in any general, in any domain. You would need some nice geometric condition on the boundary of omega. So that's what will be discussed by the end of this lecture. So basically, we will at least state, not complete proof, but very brief sketch of proof. I will state and give a brief sketch of proof that some necessary and sufficient condition that when we actually have the solvability. Okay. So yeah, that's the goal of today's lecture is, by the end I should be able to talk about that. And yeah, so in the very beginning I was talking about all these interdependencies and all, so I want to I mean about I mean so just having some continuation with that discussion, I just want you to recall. So this is something one you can prove independently. Okay, so on the so when I have a ball, a ball with center A and radius r in Rn. So in the ball, the solution was kind of much more previously known in a classical sense. So this is something what I'm trying to say. This is very fundamental. What I will now just write. And so basically, I'm talking about when the solvability of Dirichlet problem in the ball in Rn. So what is known is, for if you start with any continuous data, so continuous where in the boundary of my ball, and my functions, I mean, for now are always real valued. I will talk, but I mean, you can also think complex valued. But what you have to do, you have to split this in the real and imaginary part, and I mean, uh, do accordingly. So, what I want you to recall is when I am starting with a ball and I'm starting with a continuous data and continuous in the boundary of this ball, then I do have a solution of the Dirichlet problem star. So, so what I'm saying is there is a function h that depends on f, of course, which is harmonic on this BNAR, and also continuous up to the boundary. This is unique also, such that this HF basically extends F. Okay, so yeah, this is the one of the most classical object that you can read a proof. So this requires what you know as like the involvement of Poisson kernel, and and this is very fundamental in the sense. I mean, although in my lecture I started with subharmonic function, but you have a lot of properties of subharmonic function, and when you will see the proof actually, that very crucially depends on this existence. So this is something you have to do from scratch. Okay, so this you know, and based on this you develop basically the theory of all subharmonic functions. So this was my I mean, I was a bit concerned. This is the reason I in the very beginning was talking about all these interdependencies and all. So I mean, this is, I will just make a remark. This is fundamental, and this is required for developing the theory of subharmonic functions. I mean, please keep this in your mind. Okay, so right, this is the classical case which is known fundamentally. Now let omega be arbitrary. Okay, so yes, so let me recall what was stars. Okay, maybe let me write down here again. So basically want to solve the Dirichlet problem, that I basically want a subharmonic U, which basically uh, okay, I also have to start with some boundary data, continuous boundary data, real, and I want to solve this PD basically, right? So yeah, I kept talking about all these subsolutions and all. I mean, all this discussion of subharmonic functions was going on, and then I like in 5 minutes back, I was talking that so one may not be able to find solution at once, but one often seeks for functions which are subsolutions. So that discussion will be relevant now, because I already have discussed how subharmonic functions can be seen as subsolutions for this PD. So recall this discussion. So basically, having those sub solutions, I am now giving you a candidate that has the potential to actually solve this PD. Okay, so define. So recall I started with some domain omega and I have one boundary data f. So I'm defining this hf omega. For simplicity, you can just write it as is. And how is this defined? This is basically the supremum over these sub solutions basically. So seeing this definition now, it will probably make sense. I mean, why all this those discussions were done. So I'm taking supremum over some family, which families class of all subharmonic functions, such that this lim sup of this V restricted to boundary is dominated by F. So basically, this is supremum over B F omega, and basically this family bf omega are, you can think this as class of subsolutions. Okay, yeah, so this is my definition. So the interesting, I mean, so I mean, I don't know you like this definition or not, but after seeing the next theorem, you definitely like this, because all of this these sub solutions have been considered. Then you are taking the supremum. I mean, doing all this complicated stuff. What at the end we are getting, that is very nice. So so the theorem is saying is this H is basically very nice function. This is in fact harmonic over omega. So this is kind of very nice, I think. So uh, so this basically is making sense of all this discussion of sub solutions. I mean, why all these efforts have had been done. So at the end, you are have at the end you are getting something nice out of all these sub solutions of subharmonic functions. So this is basically a nice candidate. So yeah, so I will probably give very brief sketch of proof, but for to prove this thing basically. So okay, so in this statement, I mean, you have no, you don't need any assumption on omega. Okay, so you start with any omega and any f continuous. You can define this hf omega, and the theorem is saying this will be harmonic in the interior. So one key uh, step to prove this is the following, which is kind of important. So again, this is basically an important fact about subharmonic functions, which I had not discussed, but I want to discuss this, because this fact is the key step of this proof of theorem 2. So let me write this. So suppose you start with a subharmonic function, and you start with a ball which is inside this. Okay, so this is my omega, and I take a ball inside. And I mean, this is important, okay, that ball should be the closure of this ball should be contained inside omega. Then what happens is, I mean, u is a priori subharmonic. I mean, in terms of regularity, it can be very weird, right? But what is this fact will say, basically, I should say this as proposition, maybe not. I mean, it's much beyond some fact. uh, so what this result would tell you, that you start with something inside. You can basically do some surgery and you can modify your function u. And I mean, after modification, you will get something nice. Okay. So what I mean is, I will write down mathematically. Then there is some u hat, which is again subharmonic. Of course, I mean, doing all this surgery, you should not lose what you already have, but you should also aim to get something better. So I will get some new subharmonic function such that it's sort of uplifted. So this u hat is bigger than u what I already have. This is number one. Number two, u hat is uplifted only inside B, but outside B it is as it is. I mean, that much you can't expect. I mean, you can only expect to have the modification strictly inside. Okay, I mean, you should not expect that much more that you will modify everything. So you had equal to U on omega minus B, but the most important thing is U hat is actually harmonic on B. That is the most important. So it is a real upliftment. So I mean, a priori you could be in terms of regularity very weird, but what can be done is you can actually modify your U to some U tilde, which is at least inside enough is harmonic, which is very 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 nice, right? So yeah, so to prove this proposition, again I will not prove the detail. I will just briefly sketch the proof. So to prove this, what is very important is what I told you to recall. So this will be play a very important role for doing this. And how is that? So okay, so u I started with any subharmonic function. It may not be continuous, so, right? So you if you assume that so this is very brief sketch. So if you assume that u is continuous, then what am I getting? So this is my omega, this is my ball del b. So what I have basically, that I start with a continuous function. You just see this u restricted to b as a continuous data. And since we already know the solvability of Dirichlet problem on this ball b, you this continuous data can be extended as a harmonic function on B, and which is also continuous up to the closure of B, right? So for and I mean you just so I mean you tell this, you name this as u tilde, and you on B, and you extend this u tilde as it is. So if you start with some continuous function, this is, you can kind of see how this proof works. But in general, my u may not be continuous, but I do have upper semi continuous. So what you do is, over this compact set del b is compact. Over this compact set, you kind of approximate u by approximate u by some sequences u nu, which are continuous. This is the general case. And you appeal to your favorite convergence theorem, say monotone convergence theorem or dominated convergence theorem, and you will basically will be able to prove this proposition. But yeah, I mean, I wanted to discuss this sketch because this is very important, and this is kind of very nice that it is seeing that you can do some surgery inside your domain, which is strictly contained in your domain, and you get much better thing, right? And yeah, so now coming back to the theorem 2. So proof of theorem 2. uh, okay, so again a very brief sketch I will say. So how should I say, let me see. Yeah, again, so so what is my aim? So I have to show some, this candidate H is harmonic in omega, right? Now harmonicity is a local property. So if you start with a ball inside your domain, it suffices to show that H is harmonic in this ball, right? So you now kind of got the hint how to proceed. So you get a ball Bn, which is strictly inside omega. Now you can do these surgeries again and again, right? But you have to do it cleverly. So what one does is, so H is by definition is supremum over certain set, right? So H is the supremum over this family B. So I started with this element A. So by definition, you can extract some sequence in my family BF comma omega such that this by definition again, uh, this family evaluated at A, this increases to H at A as nu goes to infinity. So yeah, so we got something, this family of Venu, but we have information only at this single point A, not all over the ball, right? We want to say something much more. We want to say something, some information over all this ball. So right, so now how do you do that? So for that, now we have to do some further modification. So do the, so okay, by the way, this modification is sometimes referred as Poisson modification. I think I read that in some book, so it will be helpful for me to for referring this result. So we basically now do the Poisson modification. And how do we do this? So I got this family v new, right? So I basically defined one auxiliary sequence by this. So I'm defining by induction. So I am having this u1. I'm doing this Poisson modification with respect to my ball that I started with. So u1 is just v1, then u2 is, you first do the maximum of u1 and v2 and take the modification, and so on. So for instance, uj plus 1 will be, you first take the maximum u1 uj vj plus 1 and this. Now we can ask why we are doing all this maximum and all, because it's not clear. I mean, like at the end we want to see, we want to get something harmonic, right? So while doing this max thing and all, basically we are getting some monotone sequence. Okay, so what, doing all this surgery we are getting, basically we are getting some auxiliary sequence of subharmonic which are monotonically increasing, and also some information is already preserved. So at A, I still have that my uj is going to HA. Okay. Now also we have this additional advantage that this all uj's are basically harmonic on this ball I started with. So I can apply to some nice property of harmonic function I already know. So there is something called Harnack's inequality. So you have to appeal to this by Harnack's inequality for harmonic. So when I will post the note, I will write more details. So by Harnack's inequality for harmonics, I will basically get that this auxiliary sequence uj basically increases to some u for some harmonic. Okay, so we got something that's good enough. We got this u, but we still don't know whether u equal to h or not, because remember, h was my candidate. I want to see that h is harmonic. So doing all this hard work, I actually could deduce some harmonic on b, but I still don't know this. But what we know, it's easy to see, because this u basically arised out of some limit. It is easy, it is not hard to see that u is actually less or equal to h. We don't know it is equal to or not. So this is the part you can see. So we have to show that it is actually equal. So for showing this part, it requires some work. So you have to sort of do, say, another round of modification. And I mean, there is some argument, so but I'm not going into detail, but I think you got some clue that how one can proceed with this proof. So maybe you can do another round of Poisson modification and proceed. Okay, so yeah, so all the so what's my moral of story is that I start with any omega. This is my location. Yes, so I start with any omega. I define this candidate H, and this candidate is very nice. That is the moral of the story. Okay, so it is some progress or improvement towards the solvability of this Dirichlet problem. So this part is kind of solved, but it is still not clear, right, that whether it actually extends my boundary data I'm starting with. So I mean, again, as I said, I mean, it's not possible to hope this for any domain. You do need some non-trivial condition on boundary of omega. So let's move to that discussion. And any questions so far? Yeah. So let me summarize.
Uh,
Yes. Hello.
yeah, do we have any question?
No, no. So
Okay.
I think you are saying something, is it? I mean, I don't know
No, no,
who's
no. I
who.
thought someone said something. So regarding questions, so I just
I see,
asked.
I see. I
Okay.
don't know. Is it? I mean, is there any question? Okay, no, I think
Yeah,
fine.
we can proceed.
Yes, yes. So yeah, I got this right. So let me write this question again. That so I start with this data and given a domain omega, when is basically so I have this candidate which is already harmonic, but when it basically matches up to the boundary value, right? That is much more delicate part. So this is a valid question. Right. So, so to answer this, I will now write the theorem, which is basically an if and only if condition, and maybe I will, I mean, very briefly, I would briefly sketch little parts of this. So, to answer this question, let omega be a bounded domain. Then the following are equivalent. So, number one, for any continuous data. This candidate I already have. This is harmonic we already saw. But the question is when it is continuous up to the boundary with h if omega zeta basically extends if zeta. So a necessary and sufficient condition is for each boundary point there is a what you call as strong subharmonic barrier at zeta. And what do I mean by this? That is, there is some subharmonic function such that at zeta it is basically 0. Now it may not be defined at zeta, so you have to talk about in terms of lim sup. So I have this existence of subharmonic function such that it sort of vanishes at zeta, and anywhere else it has to be strictly positive. So lim sup of u restricted to every point up to the closure except zeta. So this is the meaning of strong subharmonic barrier. Okay. So I will state one more condition. So so these two are equivalent. These two are equivalent to another condition. So for each zeta there is a weak subharmonic barrier at zeta. So what do I mean that? That is, there is some u zeta which is subharmonic such that, again, like number 2, it should vanish at zeta. But I don't, I just want that you should be strictly less than 0 on omega. I don't want to demand anything, any boundary behavior on, I mean behavior on the boundary points for to be able to talk about weak subharmonic barrier. I mean, please, if you have seen this for the first time, please see the difference between two definition: strong PSH barrier and weak PSH barrier. And it's very trivial to see that strong PSH barrier is a strong subharmonic barriers are obviously weak subharmonic barrier, but the converse is not. I mean, well, if a single function may be strong subharmonic barrier, uh, sorry, what I'm saying, sorry, yeah, so any strong subharmonic barrier is definitely weak subharmonic barrier, but the converse may not be true. But what this theorem is saying, that if you are guaranteed that you at each point your weak subharmonic barrier is given, it is saying you can construct some other strong subharmonic barrier as well. It may not happen that the weak subharmonic barrier you start with, that candidate is itself strong barrier. That may not happen. But this theorem is guaranteeing the fact that if you start with weak barrier, you will be able to construct some other strong subharmonic barrier. That is the non-triviality of this statement. But yeah, and both of these barrier condition basically is characterizing the solvability of the Dirichlet problem I kept talking about. Okay, so yeah, so maybe a brief sketch of proof. Right. So seeing one implies two is sort of easy. Basically, for each you fix your boundary point zeta, and you construct. I mean, yeah. What continuous data you should take? You just take this choice, this x going to x minus zeta norm, and take a minus, because I mean we are at the end we have to I mean we need some negative psh existence and all. So this is your data is in c of del omega. So what you do is, so now what do I have? I'm proving one implies two. That means for this data f zeta, i do have some I do have some unique harmonic solution, right? So I have to construct u of zeta, then basically u zeta defined as h f zeta comma omega. So this h thing is guaranteed by assertion 1 will work. Okay, so yeah, this is 1 implies 2. So I will also briefly sketch 2 implies 1. So I think I have 5 more minutes, is it? I started 5 minutes late, right? I think 6 more minutes I think I have.
Yes, yes.
Yes. So 2 implies 1, yeah, let me sketch. So yeah, let me see how to proceed. So I have 2. That means what I have that for each boundary data, I have an existence of a strong subharmonic barrier. Okay, so I have to show that uh, each f has an extension. Okay, so I have to prove one. So start with a continuous data. Right. So the nice thing which I really like this, I mean, we already have an automatic candidate. H f omega is already there as a harmonic candidate, all you have to show that it matches up to the boundary value, and that is the delicate part. But if it's not that every time you have to appeal to have to look for a candidate and proceed. No, you already have some candidate. All you have to see, show that you have that candidate actually matches up to the expectation. So right, so I start with my data. I already have this HF. So how to show that it basically matches up to the boundary, right? So yeah, how to proceed? So yes, let me start with a boundary point. By 2, I have U zeta, a strong subharmonic barrier. Right. So, right. Now, basically, you have to show some limiting argument, right? That to show limit HF omega as x going to zeta is f of zeta. Right, if is given continuous, that's good. So I will do some epsilon delta argument. Let it epsilon can be, if epsilon is positive, then we can, my claim is we can find some constant c big enough such that, so yeah, please see this carefully. C u star. So you right. So yeah, you, this is also important. I mean, we keep saying about U star. We don't say U because you don't know whether at the boundary U is continuous or not. So we can't get rid of this upper semi-continuous regularization of these functions in the in when we study these results in potential theory. But this is kind of important. So yeah, this U star keep coming. That's why. So I can find some C such that C U star, this is less than F plus epsilon on del omega, and C U star is less than minus F plus epsilon on del omega. So so this is, I mean, you have to stare at this in equations and see. So basically, this will follow from the definition of U itself. So there are two facts basically. U is upper semi-continuous. Also, you have U is strictly negative. So you know that on the compacts, upper semi-continuous functions on the compact sets are bounded enough. So you sort of used all these facts, and you will get some constant so that all 1 and 2 are satisfied. Okay, so yeah, this you can show. Now once you have this Roman 1, this will, what is this basically saying? So it is saying C U star is, so okay, let me write down what it is saying. That it is saying C U minus epsilon. When you are seeing this function, this is basically in this family of subsolutions, and this is ensured by this Roman 1, right? So this is what we have. So that will imply that since this is now a subsolution, Cu minus epsilon will be dominated by the supremum over all subsolution, which is my favorite candidate H. So yes, I have this. Again, I already know that H is harmonic, right? Is harmonic on omega. And I also know that since it is a supremum over several candidates, and all of those candidates do satisfy some certain domination over the boundary, that will be propagated for this supremum as well. So again, this is coming from the fact that H is the supremum over the subsolutions. So these are two facts. Okay, so I have that H is harmonic. How do I write? This is harmonic, and I have this. So having both of this fact, I have the following: HF omega plus Cu minus epsilon. You see the upper regularization of everything. This is basically F minus F, and this is coming by 2. if you see what I mean. So from 2 I had some relation, and for h, the function h alone, I have something. So this is nothing but 0. So I got some information. Now this this object this object is subharmonic in its own. So and I have some information of this over the boundary. So by maximum principle, I have that hf, this the information is propagated on omega. Okay, so right, so let me write it as b. So from a and b, I get that what do I get? Cu minus epsilon less or equal to hf omega Cu. One second, have I done something wrong? Minus Cu plus epsilon. Okay. Yeah, now what do I do? Now recall, okay, so U is U zeta, okay? So U zeta I should write. Because recall I started with some boundary point zeta, and I have this strong barrier U zeta. So from this I can just show that lim of hf x is 0, as U zeta is a strong barrier. Right. So, so that my boundary point was arbitrary. So, what you can actually establish this point. This is basically established. Okay. So, 2 implies 1 is established. So, this is a sketch. Now, it remains to show 2 implies 3. So, as I was saying that 2 2 implies 3 is obvious. Now showing 3 implies 2 is of course not obvious, so it does require some effort. So I will not talk about that, but this is true. So maybe I can write some outline of the proof, how this, or some reference that how to, I mean, this requires some effort, so I will not talk about that. So yeah, so I think we could basically have see some characterization that when we have the solution of this PD star or Dirichlet problem. So basically we characterized so as we start bounded domains in Rn, we know some necessary and sufficient condition on the boundary of those domains, such that when any continuous data on the boundary has some harmonic extension inside. So yeah, maybe I should stop here, and you can ask that what I mean again, this is a condition on the boundary, but it may not see very geometric, but there are like huge class of domains with some nice geometric objects which do satisfy these properties. So for example, any domain omega with C1 smooth boundary satisfies this barrier condition, has this. So basically what was claimed is both weak and strong barrier are equivalent. So I would just write that has what happened, oh, my pen is not working. So yeah, so what I'm saying that there, I mean, this if you're seeing this for the first time, it might seem abstract, but basically domain with reasonably nice boundary actually satisfy this barrier property. So any domain omega with C1 smooth boundary has this. I don't know why my pen is not working. Maybe there is a lag. Oh, it's not, it's just not working, I don't know. So yeah, I will write down the. I will complete the note and send you. But the pen is not working somehow. So yeah, so any domain, even with much Lipschitz, if your domain has boundary of your domain has Lipschitz boundary, then again both of these properties 2 and 3 will be satisfied, and at the end what you get, that solvability of the dirichlet problem. So convex domains, for instance, convex domains always have Lipschitz boundary. So for any convex domain, your Dirichlet problem is solvable. So yeah, maybe I will stop here.
Okay, thank you, Annapurna. Do we have any question? Okay, so if not, we will close this session. We will meet
Sure.
in the next session.
Yes.
Okay, yeah, thank you, Annapurna.
Yeah. Thank you.